10 billion fishing hooks are manufactured in global industrial facilities every single year. This immense volume is the result of a production system that operates at a specialized high-speed cadence. Why does such a massive manufacturing scale exist for a tool that appears so basic? The global fishing tackle ecosystem is worth more than $15 billion, and this tiny component is its most widely consumed element. Every maritime operation, from the smallest recreational boat to large commercial fleets, relies entirely on a single piece of metal that often weighs only a few grams. But this is just the beginning. One can notice how wire drawing machines within vast metalworking facilities continuously reshape raw material. Mechanical dies bend each steel segment in a fraction of a second to create the necessary geometry. Heat treatment furnaces then refine the internal grain structure of the metal to establish a critical technical balance between absolute hardness and necessary flexibility. It only looks obvious that a small hook would be simple to make, but in reality, every movement of the machinery is engineered for extreme load-bearing capability. A high-quality hook can withstand between 300 and 500 pounds of pulling force. This resistance is roughly comparable to the weight of a small piano. Such a strength-to-weight ratio is a characteristic usually reserved for advanced aerospace or structural components, yet it exists within an object most people rarely consider. High-carbon steel serves as the foundation for the entire process. The material arrives at the production line as a coil compressed into tight, heavy loops. This coil is mounted onto a rotating payoff reel, which slowly and steadily feeds the wire into the start of the manufacturing sequence. As the steel unwinds from the spool, it retains a natural curvature from its time in storage, requiring it to pass immediately through a wire straightening machine. The equipment gradually removes these deformities using a series of offset rollers. These rollers apply small but continuous corrective pressure, guiding the wire back into a stable linear form without distorting its circular cross-section. Once the wire is perfectly aligned, it moves through a driven feed system that maintains a consistent delivery speed. At the end of this specific line, the material enters an automatic cutting unit. One can notice how the blades cycle with rapid precision. Depending on the specific hook size being produced, each steel segment is typically cut to a length between 1 and 3 inches. The entire operation runs continuously at high speed to meet global demand. A standard feeding system can process hundreds of feet of wire every 60 seconds. The process is only gaining momentum. This configuration allows the machinery to produce anywhere from several hundred to more than 1,000 steel segments every minute. The moment the cutting blade closes, the straight steel pieces slide down a metal chute and drop into a circular collection tray positioned directly below the exit point. Dust and microscopic metal shavings settle as the tray fills. When a sufficient number of pieces accumulate in the tray, workers transfer the segments into a longer container for the next phase. The raw steel segments now sit in uniform rows, ready for the shaping processes that will transform them into functional tools. 150 millimeters is the standard length of the straight steel segments as they transition toward the critical stage of point formation. Why is such high velocity required during the initial grinding process? It would seem a slower rotation would allow for more delicate handling of the metal. But without high-speed abrasion, the steel would tear rather than shave, leaving a jagged surface instead of a surgically sharp edge. Each individual piece is mechanically fed into a high-speed grinding machine, where a rapidly rotating abrasive wheel executes the material removal. It is visible how the tip of each steel segment is pressed lightly against the spinning surface with microscopic precision. One can notice how the grinding wheel removes extremely thin layers of metal, gradually shaping a smooth and perfectly tapered point. The process is only gaining momentum. Tiny sparks scatter at every millisecond of contact, acting as a visible indicator of the intense friction separating material from the core. At the same time, automated systems must monitor the pressure and the exact duration of contact to prevent the steel from overheating. It looks superficially simple to sharpen a wire, but in reality, thermal deviation can ruin the structural integrity of the metal. The material is quickly fed into an automatic forming machine once the sharpening is complete. Each blank is guided into its next position through a precision-engineered channel. The equipment gradually secures the segment against a specialized steel die to ensure there is no lateral movement as mechanical force is applied. But this is just the beginning of the transformation. End pressing serves as the primary operation inside the die, where controlled hydraulic pressure slightly flattens the tail of the steel segment. This specific action expands the cross-section of the metal just enough to establish a wider and stronger surface. This preparation is essential for the subsequent formation of the eye, which will eventually serve as the attachment point for the fishing line. Immediately after the tail is flattened, the sharpened end of the segment passes beneath a micro stamping blade to produce the barb. The entire mechanical sequence, from positioning to stamping, runs in a continuous cycle lasting less than 1 second. The camera glides along the assembly line as the die opens, allowing the newly formed hook to slide off the platform. The finished components drop into a collection tray below, marking the end of the shaping phase. The material is ready to move to the next processing stage without haste. 1,400 to 1,600 degrees Fahrenheit is the temperature range the continuous hardening furnace reaches as it receives the formed steel. Why is such intense thermal exposure required for a simple metal hook? It would seem that the shape alone determines its function, but without this specific heat, the steel lacks the structural integrity to withstand a strike. This thermal energy causes the internal crystal structure of the metal to reorganize at a microscopic level. But this is just the beginning. The hooks move along the metal conveyor with the mechanical precision of a clock. One can notice how the material transitions from the furnace directly into a controlled cooling environment. This rapid quenching locks the newly formed microscopic structure into place, resulting in a dramatic increase in hardness across the entire surface. It looks superficially simple to harden the steel in this way, but in reality, this state creates extreme brittleness. A hook that is only hardened would fracture like glass under the sudden tension of a moving weight. The process is only gaining momentum as the items proceed to the tempering phase. Here, the steel is reheated to a lower, precisely calculated temperature to solve the problem of internal stress. This stage does not aim for hardness, but rather restores a measured degree of toughness to the metal. It is visible how the conveyor carries the parts through these thermal cycles until residual oils and contaminants are eventually stripped away. Everything only gets more complicated as the metal moves toward the chemical preparation zone. Acid treatment serves as the primary method for removing oxide layers and impurities left by the high heat. Why must the metal be stripped of its outer film so aggressively? The surface needs to become chemically active to ensure the next layer does not merely sit on top. A clean surface allows the protective coating to bond tightly to the steel grain. Transition to the next level occurs in the electroplating bath, where an electrical current deposits a thin barrier of nickel, black nickel, or tin. The equipment gradually moves the hooks through a repeating sequence of tanks. It is visible how the parts descend into acid, then rinse, then plate, and rinse again to ensure no chemical residue remains. This prevents the metal from reacting with water or oxygen once it leaves the factory. After the final immersion, the hooks enter a zone where clean water flushes the surface and heated air evaporates moisture. The metal surface appears brighter and more stable, signaling that the chemical transformation is complete. One can notice the camera glides along the vision inspection system, where every hook is scanned for defects. Representative samples are taken from each batch and placed into a tensile testing machine for a final verification of strength. Force is increased to the design threshold, measured in hundreds of pounds to confirm the hook will not straighten or snap. Random checks are performed on the sharpness of the points and the exact positioning of the barbs to maintain consistency. The process concludes this phase as automated systems count the hooks into preset quantities for protective packaging. The packages are labeled and sorted by product code before being placed into heavy cartons. The finished material is now ready to move to the global distribution networks without haste. 8 to 10 layers of carbon fiber are processed simultaneously during a single automated cutting cycle to maintain industrial productivity. Why is such a high volume of material handled at once? It would seem that cutting each sheet individually would ensure greater precision, but without stacking the layers, the production rhythm would stall, and the chemical stability of the heat-reactive resin would be compromised before the rod even reaches the forming stage. The primary materials for the rod blank consist of carbon fiber and fiberglass prepregs. These fibers arrive already impregnated with a specialized resin designed to harden only when exposed to extreme temperatures. If the material remains at room temperature for an extended duration, the resin begins curing prematurely, rendering the entire batch useless waste. Because of this extreme sensitivity, all prepreg materials are kept in specialized cold rooms at temperatures below 32 degrees Fahrenheit. One can notice the frost on the storage containers as they are removed only at the exact moment they are required for the assembly line. As soon as the prepreg leaves the cold storage, the clock starts ticking for the production team. The material is unrolled and laid flat onto a massive cutting table, following every technical outline and geometric specification provided by the engineering department. But this is just the beginning. A technician measures the sheets by hand and carefully aligns the material edges before the machine executes each pre-programmed cutting pattern with controlled precision. Accuracy is preserved down to fractions of an inch during this process. Carbon is rarely cut in straight lines. Instead, it is shaped into complex triangular forms or distinct diagonal patterns. It only looks obvious that these shapes are for aesthetics, but in reality, this specific cutting geometry controls exactly how force travels along the length of the rod when it bends under a heavy load. A single piece cut off by even a fraction of an inch can shift the entire flex point of the rod, destroying its intended action. The material must then be positioned with absolute precision onto the mandrel. This stainless steel shaft serves as the internal forming mold for the rod blank. The equipment gradually rotates as the mandrel is typically treated with a non-stick release agent to ensure the finished blank can be separated cleanly without surface damage after the heating cycle. Once a thin layer of adhesive is applied evenly along the steel shaft, the technician utilizes a small heated iron or a localized thermal tool to hot tack the first layer of material into its designated place. The process is only gaining momentum. Each carbon piece is aligned carefully along the center line of the mandrel, squared at both the tip and the butt ends, and only then secured. One can notice how the technician's hands move with deliberate slowness to prevent any air pockets. If the first layer is positioned off-center by even a millimeter, every subsequent layer of the rod blank will inherit that misalignment. Everything gets more complicated further on, yet there are no robots or laser guides involved at this critical stage. Everything depends entirely on the trained eye and manual experience of the technician. Metal and fiber meet in a cold state, waiting for the thermal transformation that will bond them into a single structural unit. The prepared mandrels are now ready to be moved toward the rolling stations where the final profile of the rod will be established. 100% of the structural integrity depends on the technician's trained eye and the depth of their mechanical experience. Why is such a high level of manual control required during the initial wrapping? It would seem that an automated arm could apply the fiber with more consistency than a human hand. But without the tactile feedback of a master craftsman, the subtle variations in the tension of the carbon sheets would lead to internal microscopic gaps, rendering the rod brittle under heavy loads. The rod truly begins to take shape at the exact moment the steel mandrel is placed onto the rolling table. One can notice how the machine rotates at a slow, controlled speed while each layer of carbon fiber is wrapped around the metallic core entirely under the command of the operator. This includes everything from the radial rotation speed and the specific hand pressure applied to the precise stopping points in the exact instant the next layer is laid down. As the core turns, the fiber layers tighten against one another with the hiss of overlapping material. But this is just the beginning. The material edges closely, and the rod gradually lengthens and tapers, following a geometry that has already been carefully calculated in the design phase. Technicians add reinforcement layers at high stress zones, specifically near the handle area, once the primary layers are complete. These reinforcements are not applied simply to make the rod thicker or more rigid. In reality, they are used to fine-tune how the tool feels during the kinetic energy transfer of casting and while fighting a fish. The process is only gaining momentum. 100% of the carbon fiber layers and reinforcement plies must be fully wrapped before the rod blank moves into the heat-resistant tape wrapping stage. The factory utilizes nylon tape, cellophane tape, or specialized vinyl tape to tightly bind the entire length of the blank before thermal processing begins. The equipment gradually secures the structure for the furnace. The mandrel is mounted onto a specialized wrapping machine where it rotates steadily. It is visible how the tape is applied in a continuous spiral, with each pass overlapping the previous one under consistent pressure from one end to the other. The purpose of this step is to lock the shape of the rod in place and keep every carbon layer pressed firmly together throughout the high-temperature heating cycle that follows. Everything only gets more complicated as the thermal preparation concludes. As the tape tightens, the material beneath is compressed evenly, creating a uniform wall thickness along the entire three-dimensional length of the blank. At this stage, the steel mandrel acts as the internal mold, while the tightly wound tape functions as the external mold, holding the structure stable as it prepares for the curing phase. The rod blank sits ready for the oven, held in a state of high mechanical tension. This concludes the primary shaping stage, opening the road to the final chemical transformation. 140 degrees Celsius is the typical temperature set within the curing ovens for the rod blanks. Once the mandrels carrying the carbon fiber components are secured with heat-resistant tape, they are hung onto specialized racks and moved into the thermal chamber. Why must the heating cycle be monitored by integrated computer systems with such precision? A simple manual adjustment would seem sufficient for such a task. However, the software ensures that the temperature rises with absolute uniformity and remains stable, preventing any thermal fluctuations that could compromise the material. The curing phase generally lasts for 2 hours, providing sufficient time for the heat-reactive resin to undergo a complete transformation. But this is just the beginning. cooling. Inside the sealed environment of the oven, one can notice how the resin begins to flow as it reaches its activation point. It spreads evenly between the individual carbon fiber layers, bonding them into a singular, unified structure through a complex chemical reaction. What were originally separate sheets of material now merge into a rod blank that is nearly monolithic in its physical properties. It gets more complex further on. Before the application of heat, the blank remains pliable enough to be removed or adjusted if a technician identifies an error. But in reality, once the thermal cycle is complete, any prior deviation or misalignment becomes permanently locked into the internal architecture of the rod. For this reason, factories enforce extremely strict technical control over the duration, the specific temperature, and the overall stability of the oven environment during this critical production step. The process is only gaining momentum. When the heating cycle concludes and the rod blank begins to cool, the mandrel extraction stage commences. The component is transferred to a dedicated separation machine designed for high-tension tasks. The metal mandrel inside is clamped firmly by a heavy-duty holding mechanism while a pneumatic pulling arm engages. One can notice the slow mechanical movement as the arm applies a steady and powerful force to draw the metal core out from the center of the carbon tube. The pulling force must be of sufficient magnitude to overcome the physical friction between the surfaces, yet it must remain smooth and precisely calibrated. This prevents any deformation of the carbon structure that has only just finished its curing cycle. If the earlier heating process was executed correctly, the mandrel will slide out cleanly from the interior. This leaves behind a completely hollow rod blank with consistent wall thickness. At first glance, the extraction appears to be a simple mechanical pull, but any deviation in the resin distribution can make extraction difficult or even damage the outer surface of the part. The equipment gradually releases the tension once the core is fully removed. Transition to the next level. At this specific point, the technician performs a quick but vital inspection of the blank for straightness and uniformity. This stage of quality control relies entirely on the trained eyesight and tactile feedback of the operator, utilizing experience built through years of handling composite materials. The material is ready to move to the next processing phase without haste. 100% of the outer wrapping tape must be removed from the blank once it has reached a state of complete cooling. Why is the removal of this sacrificial layer performed with such specific manual orientation? The technician peels the material back by following the exact spiral direction established during its initial application, unwrapping the strip in a continuous motion from the tip toward the butt of the rod. This prevents any sudden tearing of the carbon fibers that have just solidified. A rhythmic unwrapping reveals the raw surface of the blank, which is covered in distinct spiral marks, small structural ridges, and a specific roughness formed under the intense pressure of the compression process. But this is just the beginning. The camera glides along the length of the rod as it is moved to the cutting station for the first stage of final shaping. Precision at this stage is measured in fractions of an inch to ensure the rod meets its design parameters. The technician places the composite rod onto a specialized support fixture, aligning it with absolute precision along its central axis before feeding it into the cutting mechanism. It is visible how the diamond-tipped blade rotates at a constant steady speed, shearing through the hardened resin and fiber to remove excess material from both ends simultaneously. This mechanical calibration brings the blank to its exact standard length, preparing it for the more refined surface treatments that follow. Everything only gets more complicated as the blank enters the dual-stage grinding and sanding phase. Dry sanding serves as the primary abrasive process, designed to break down the larger resin ridges and smooth the sharp edges of the spiral imprints left by the compression tape. One can notice the technician rotating the rod evenly by hand, maintaining a constant speed to ensure the abrasive treatment remains uniform around the entire 360-degree circumference. It only looks obvious to sand the surface, but in reality, any uneven pressure at this stage would create flat spots that ruin the rod's action. Transition to the next level occurs as the process shifts to wet sanding. Water flows continuously over the rod, reducing friction and instantly carrying away fine resin dust that would otherwise clog the abrasive grain. This fluid medium allows for much finer control over the sanding pressure, resulting in a surface that is perfectly smooth to the touch. After the surface finishing is complete, the individual rod sections are transported to the joint fitting area for a critical alignment inspection. The technician inserts the thinner tip section into the corresponding butt section while maintaining the correct structural orientation. He then performs a series of gentle twists and controlled shakes of the entire assembly to feel the internal tightness of the connection through his fingertips. A joint that meets the engineering specification must engage evenly across its entire surface area, showing no signs of looseness or physical play. Why is this manual tactile check considered considered so vital to the integrity of the product. The assembly must remain silent and rigid even when moved under stress. This is because a deviation of just 0.04 of an inch at the joint interface can completely disrupt the continuity of force transfer along the blank. Because the structural transition must be seamless, any gap would lead to a concentrated stress point and eventual failure under load. Once the fit is approved by the inspector, the rod sections are separated once more and organized into bundles according to their specific model and length. These bundles are secured neatly with industrial ties and staged for transport. The material leaves the fitting area, transitioning into a calm stage as it is sent to the painting workshop for its final aesthetic treatment. 100% of the surface area must be free of imperfections before the rod blank enters the specialized paint shop. The component is secured onto a rotating machine that maintains a constant angular velocity to ensure the coating applies evenly around the entire circumference. Why is the initial application almost always a white base primer? This layer serves to unify the texture of the composite material and acts as a reflective foundation that increases the color vibrancy of subsequent coatings. But this is just the beginning. It is visible how the rotating blank receives its primary color layer once the primer has fully stabilized. Fluorescent pigments are frequently utilized during this phase to maximize the visibility of the equipment during outdoor operations in low light or overwater environments. One can notice how the sprayer oscillates to maintain a consistent micron thickness across the length of the tool. At first glance, the color choice seems purely aesthetic, but in reality, it serves a critical safety and tracking function for the user. Customizations are integrated at this point to meet individual technical specifications for the final order. The process is only gaining momentum. The application of a clear urethane top coat signifies the technical conclusion of the exterior finishing. Technicians spray or wipe this final substance in an even film to establish a smooth protective barrier against physical scratches, ultraviolet radiation, and the corrosive effects of saltwater moisture. The rod blank is then transitioned into a temperature-controlled drying room where the chemical coating is allowed to cure and stabilize. And this is not the limit. The equipment gradually undergoes a transition as it is moved into the handle assembly zone. Each component of the grip system is installed entirely by hand with manual precision. The technician applies specialized adhesive along the surface of the blank before carefully sliding each handle section into a designated coordinate. Specific materials such as ethylene vinyl acetate foam, cork tape, or specialized heat shrink tubing are selected based on the specific model requirements. It gets more complex further on. The installation of the reel seat follows, which is the structural component responsible for securing the fishing reel to the spine. Perfect alignment along the central axis of the rod is mandatory during this procedure. Why must the reel seat be positioned with such jewelry-like precision? Even a slight deviation in the angle of the seat can create ergonomic discomfort and negatively alter the distribution of force when the rod is under a heavy mechanical load. Once the technician fixes the seat in its final orientation, the butt end of the tool is sealed with either a protective cap or a gimbal. At this stage, the composite tube is no longer a simple raw material, as it has acquired the balance and tactile character of a finished instrument. The material is ready to move to the next processing phase without haste. 100% precision is required during the final assembly of a professional fishing rod. After the blank has been painted and the handle is fully installed, the critical process of guide installation commences. Why is the placement of these components so vital to the final product? The spacing and alignment of each guide determine the exact path the fishing line takes and dictate how the mechanical load is distributed across the carbon fiber during a catch. One sentence later, the answer becomes clear as the technician marks each position according to a calculated design layout, ensuring the rod will not snap under extreme tension. Each individual guide is placed onto its designated mark and aligned by eye along the central axis of the rod. But this is just the beginning. The technician secures the guide foot by wrapping fine thread around it with steady manual tension. One hand maintains the position of the metal guide, while the other ensures the thread is wound evenly and tightly against the blank. One can notice how every individual wrap must sit cleanly beside the next without a single gap or overlap in the fibers. After all guides are wrapped in this manner, a final visual inspection is performed along the entire guideline to confirm perfect straightness and balance. Everything only gets more complicated. The rod moves immediately into the epoxy coating stage once the thread wraps are secured. It seems simple at first glance, but in reality, the resin must penetrate every fiber fiber of the thread to bond firmly with the rod blank. The technician uses a brush to apply a base layer of epoxy over each individual wrap. One can notice how the resin saturates the thread, creating a unified structure between the guide and the rod. The process is only gaining momentum. Next, the rod is placed onto a rotating rack or a turning drum. This continuous motion allows the liquid epoxy to level itself perfectly around each guide under the influence of gravity and rotation. The rods then pass through a flow of hot air or an ultraviolet curing chamber. These two elements, heat and ultraviolet exposure, serve to partially cure the epoxy and stabilize the wraps before a second application. A final glossy coat of epoxy is then brushed on to create a thick, durable, and protective surface. In a single day, the factory consumes thousands of ounces of finishing material during this specific phase. Dozens of rods rotate simultaneously on each drying rack, ensuring the finish cures with absolute uniformity. At this point, the tip section and the butt section are joined together for the very first time. The technician inserts the thinner tip into the butt section using the correct orientation. A gentle twist is applied to verify the physical fit of the joint. The connection must engage evenly, maintaining a tolerance that is neither loose nor excessively tight. Transition to the next level. The assembled rod is placed onto a dedicated inspection table to verify axial straightness. The technician rotates the rod slowly, observing with the naked eye and feeling the surface by hand to confirm that the axis remains true. This manual check ensures there are no abnormal bends or structural warps in the finished assembly. It does not end at this stage. A controlled load is applied to the rod for a flex test to verify strength and balance along its entire length. Once the structural integrity is confirmed, the entire rod is wiped down to remove fingerprints, fine dust, and any excess adhesive residue. The surface is examined under strong, high-intensity lighting to detect any remaining scratches or minor imperfections. When all quality criteria are met, the rod is tagged and placed into a protective sleeve. The finished product is then packaged and moves toward the shipping bay. The rod leaves the production environment, ready for use on the water.